In the previous session of calculus and its role in AI, we learned about functions and limits usage in AI. In this session, we will understand the role of derivatives and partial derivatives in AI. 3. Derivatives. Derivatives measure how quickly a function changes. Mathematically, it represents the rate of change of one variable with respect to another. In artificial intelligence, derivatives measure how much the prediction error changes when a model parameter changes. This information is critical because it tells the model which direction will improve its predictions and which direction will make them worse. During training, if increasing a parameter causes the error to increase, the derivative signals the model to reduce that parameter. If the parameter reduces error, the derivative encourages the model to increase it. This feedback mechanism is what allows AI systems to learn automatically from data. Derivatives are widely used across many areas of AI. In deep learning, they determine how neural network weights influence the loss function. In machine learning optimization algorithms, derivatives guide parameter updates. In reinforcement learning, derivatives help improve decision policies through policy gradient methods. A simple analogy is driving a car on a hill. The slope of the road tells you whether the car should accelerate or slow down. If the road slopes upward, you increase power. If the road slopes downward, you may reduce acceleration. Derivatives measure this mathematical slope, and AI uses this slope information to adjust model parameters. To explore derivatives further, learners often study automatic differentiation, numerical derivatives, and higher-order derivatives, which all play an important role in neural network training and optimization algorithms. 4. Partial derivatives. Partial derivatives extend the idea of derivatives to multiple variables. They measure how a function changes when one variable changes while all other variables remain constant. Artificial intelligence models usually contain many input features and millions of parameters. Partial derivatives help the model understand how each individual parameter affects the overall prediction error. For example, in deep learning models, each weight contributes slightly to the final output. Partial derivatives calculate the influence of each weight on the loss function, allowing the training algorithm to update parameters correctly. In computer vision systems, partial derivatives help evaluate how pixel features affect classification. In natural language processing models, they help adjust word embeddings so that language representations improve over time. A helpful analogy is adjusting settings on a television. You may adjust brightness, contrast, or volume independently. Changing one setting affects the experience without altering the others. Partial derivatives measure the effect of one adjustment at a time. Further exploration often includes gradient vectors and multivariable optimization, which are central ideas in neural network training. That's how derivatives and partial derivatives power the training of AI models. Follow SimplfyTech to discover more calculus concepts that help AI become smarter and more efficient.